Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over another calorimetry problem. So let's go over this. So in this problem we have a coffee cup calorimeter that contains 400.0 grams of water and 25 grams of ice at 0.0 degrees Celsius, when a 30.00 gram scoop of calcium chloride, also at 0.0 degrees Celsius, is added to the ice water. The calcium chloride dissolves as shown. Right, so here's the equation for the dissolving of the calcium chloride. So we have calcium chloride solid dissolving in water, so the ions separate and becomes calcium ions and chloride ions. The heat produced by this reaction is enough to melt all of the ice and warm up the resulting calcium chloride solution. What is the final temperature of this solution? Assume that there is no heat loss to the surroundings, and the specific heat of the calcium chloride solution is going to be 4.12 joules per gram degree Celsius. And then they give us a bunch of other information that we may be able to use. Now, they give us the specific heat of steam. Well, if we look at we don't know what the final temperature is at the moment, but we could use that if we need to. Specific heat of water, specific heat of ice, and the heat of fusion. Okay, and the heat of vaporization if we need it. So let's go ahead and lay out what we need. So whenever you're doing these sorts of calorimetry problems, you need to first figure out what is giving off heat, what is absorbing the heat. Because we're assuming here that all of the heat that was created or transferred is not lost in the environment. So all of the heat that's produced or released or transferred is going to be then absorbed by something else. Nothing is lost. So we need to figure out what's producing the heat, what's giving off heat, and what is absorbing the heat. So we've got a reaction going on here, a dissolving. We're told that it releases heat. So we're going to have Q for each of those heat absorptions and heat releasings. So remember, so if I write down here Q1, so that's a quantity of heat that's either being released or absorbed. In this case, if we look at the reaction, this is heat being released. So we're going to call this Q1. That's going to be Q of the reaction. Okay? So the reaction is giving off heat. Well, what's absorbing the heat? Well, we've got ice water. There's ice in the water. We're told that that is going to melt. That this reaction is going to produce enough heat that's going to melt the ice. So the ice is absorbing some of that heat in order to melt. So the Q2, our second Q value, is going to be the Q of the ice, the amount of heat absorbed by the ice to get it to melt. Next, we're told that the rest of the heat is going to warm up the resulting solution. So we have this calcium chloride solution that is also going to absorb some heat. That's going to be Q3. So Q3 is going to be the heat of the solution. So that's going to be, we're going to call that Q of the solution, the amount of heat absorbed by the solution. And that's pretty much all we have. There's no more Q values. Okay? So if there are other Q values, we would label them Q, Q3, Q4, Q5, and all that. And then we would describe them similarly. So here we have 3 Q values. So now what we need to do is set up our equation. So remember, we're assuming here that all of the heat released by one object is being absorbed completely by the others. So remember, if we had 2 Q values, your simple calorimetry problem would have two Q values, right? One thing is releasing heat, one thing is absorbing heat. And so you would have Q1 equal to Q2. But if Q1 is releasing that heat, that would be negative. Q2 is absorbing that heat. So here, the amount of heat released is equal to the amount of heat absorbed. No heat being lost to the environment. So this works. However, we have three Qs. So here, we're going to have the Q, the reaction is releasing heat, so that's going to be Q1. But then the Q of the ice and the Q of the solution, 2 and 3, are both absorbing. So in this case, we're going to have two Qs on this side, Q2 and Q3, right? And then you could use this to solve the problem. Now, I like to move all of the Qs to one side. So I'm going to take the negative plus Q1. I'm going to add Q1 to both sides plus Q1. So then what I get here, the negative 1, positive 1 is going to cancel out. So I'm going to get 0. 0 is then equal to Q1 plus Q2 plus Q3. So all of your Q values are on one side. Again, this makes sense because all of the heat that is being released is going to be negative. That's equal to the amount of heat being absorbed, which is positive. So if they're equal and opposite, all of these added together should end up being equal to 0. So I like using this form. You can use this form if you want, it doesn't matter. But I like using this. It works out all the same. You just need to make sure that you're making sure that you're adding the right numbers. You're making sure that if there's a temperature change, you got final minus initial, right? Otherwise, you're going to get a sign difference and it's going to mess your calculations up. So just make sure that you have everything correct. Okay, so I'm going to go ahead and erase this. I'm going to rewrite this up here. So I got 0 is equal to Q1 plus Q2 plus Q3. And so now I can replace Q1, Q2, 3 with these because I've already identified what they are. So this is going to be Q. 0 is equal to Q1, which is Q of the reaction. That's the heat released by the reaction. Plus Q2 is the heat absorbed by the ice. So we're going to call that Q ice. And Q3 is the heat absorbed by the solution. So we're going to call that Q solution. Okay, I have my equation. Now all I need to do is figure out what formulas I need for each of these Q values. Okay, so Q of the reaction. So Q of the reaction, notice I have the heat of the reaction here, but this is per mole, right? So delta H, this is per mole. So that's going to be delta H of the reaction, but Q of the reaction is going to be the heat released, which is going to be joules or kilojoules. In this case, I have kilojoules. But delta H, the heat of the reaction, is kilojoules per mole. I don't want per mole. I want just the energy unit. I want the heat. So in order to get Q, the heat, I need to take this and multiply it by moles. N is the number of moles. Okay, so now I have the heat of the reaction in moles. Now, that's going to be good, but notice that I have everything in grams. I have 35 grams of the calcium chloride. I got grams of ice. I got everything in grams, but I got this in moles. Now, one of the things we can remember is, one, I can take the number, there's a couple ways you can do this. Either way is fine. I can take the number of grams of the calcium chloride, convert that into moles, and then I got my moles. Okay, that's one way. That's a perfectly fine way. Another way is, if you remember, well, what is molar mass? Molar mass is equal to the mass in grams divided by or per mole. Number of moles is N. So molar mass is the number of grams per 1 mole, or per number of moles, right? So here I have molar mass in terms of mass in grams divided by moles. Now I can solve for N. Notice I have N here. I can solve this for N. So I go multiply both sides by N. So N cancels out. Now I have N times the molar mass equal to the mass in grams. And now to get N by itself, I divide by the molar mass. So that's going to cancel out. Now I have N, the number of moles, is equal to the mass in grams divided by the molar mass. So now this is pretty much the same thing. So I'm basically doing the conversion, but now I'm putting it into the formula. So now this is going to be equal to the change in the enthalpy of the reaction multiplied by, instead of N, it's going to be the mass over the molar mass of the calcium chloride. So that's the formula I can use for Q of the reaction. Okay, what about the Q of the ice? Well, there I'm going to need the heat of fusion of ice. Here they give me the heat of fusion of ice. So there it's going to be delta H fusion. But notice here the units of the heat of fusion. It's the joules per gram. Joules per gram. So remember, again, Q is the heat absorbed by the ice. That should be in joules alone. That should be a heat unit alone. But this is a heat unit per gram. So in order to get the unit joules by itself, I'm going to have to multiply by grams the mass of the ice. So here, I'm just going to multiply by the mass of the ice in grams. And so there's my formula to get the amount of heat absorbed by the ice. Finally, this is going to be the amount of heat absorbed by the solution. Well, what's going to be? That's going to be your Q equals MCAT, because I've got the mass of the solution. Well, what's the mass of the solution? Well, the mass of the solution is equal to everything mixed together, right? The solution is a mixture of what? It's a mixture of the scoop of the calcium chloride that I added. It's a mixture of the 400 grams of water and the 20 grams of ice. So the solution mass is going to be the mass of all those together. So it's the mass of the water plus the mass of the ice plus the mass of the calcium chloride. So all of those added together is going to be 400 grams plus 25 grams plus 35 grams. Let me give myself some room here. So I'm going to add those down here. So it's going to be, what do I have? 400. So 400.0 grams plus the 25.0 grams plus the 35.00 grams, 35.00 grams. And when I add all of this together, I get 460 grams. And for the number of sig figs, it's when you're adding and subtracting, the rule is that the number of decimal places in your answer should be the same as the least number of decimal places in the measurements you're adding. So this has 1. So the last digit here is in the tenths place. The last digit here is in the tenths place. The last digit here is in the 100th place. So that means the last digit for my answer should be in the tenths place. Okay, so that means that the total mass of your solution is 460.0 grams. Okay, so that means that this is going to be equal to the mass of the solution. I'm going to put S for solution, multiplied by the specific heat of the solution, multiplied by the change in temperature of the solution. And remember, change in temperature is equal to final temperature minus the initial temperature. Now we are ready to plug everything into our equation. Let me go ahead and erase some of this stuff to give myself some room. Okay, so I have the heat of the reaction. So 0 is equal to Q of the reaction. Well, what's the form of the Q of the reaction? It's going to be the heat of the reaction multiplied by the mass of the calcium chloride I added divided by the molar mass of the calcium chloride. So 0 is going to be equal to the change in the enthalpy of the reaction multiplied by the mass of the calcium chloride divided by the molar mass of the calcium chloride plus the Q of the ice, which is going to be this formula here, the heat of fusion multiplied by the mass of the ice. So delta H of the fusion multiplied by the mass of the ice. And then added to that, going to be the Q of the solution, which is going to be Q equals MCAT. So the mass of the ice times the specific heat of the ice, mass of the solution times the specific heat of the solution times the temperature change of the solution. So that's going to be mass of the solution times specific heat of the solution times the delta T. And again, delta T is going to be final minus initial. So let's go ahead and put that in. Final temperature minus the initial temperature. And so here's my equation. So now I don't need this anymore. I can get this out of the way. Okay. So now I'm going to just plug in all of the things that I know, all of the values that I have here. So 0 is equal to the heat of the reaction. That's going to be negative 81 kilojoules. Now, since this is in joules and this is in joules, everything's in joules except for this. So let's go ahead and convert this to joules. So since I have moles, since I have kilojoules on the top, I'm going to multiply this by a conversion factor. I know that 1 kilojoule is equal to 1,000 joules. I put kilojoules on the bottom, so it cancels out kilojoules on top. And so now this is going to be equal to negative 81,000 joules per mole. So now I can put that here. So this is going to be negative 81,000 joules per mole multiplied by the mass of the calcium chloride, which is 35.00 grams, divided by the molar mass of calcium chloride. If I look that up, the molar mass of the calcium chloride is The molar mass is going to be 110.98, so 110.98 grams per mole. And so we can see here that, well, I'll get to the units later. And we're going to add to that this one, so the heat of fusion, which is 334 joules per gram. So 334, let me rewrite this. So 334 joules per gram. And that's going to be multiplied by the mass of the ice, which we're told 25.0 grams. So 25.0 grams. And then finally, we're going to add the third part. So we got the mass of the solution. Again, the mass of the solution is all of the masses added together, 460.0 grams. So I'm going to write that down here. So 460 grams multiplied by the specific heat of the solution. And we're told that the specific heat of the solution is to be assumed, where is it? 4.2 joules per gram degrees Celsius. So 4.2 joules per gram degrees Celsius multiplied by the temperature change. And that's going to be the final temperature minus the initial temperature, which we're told that everything was at 0.0 degrees. So that's the initial temperature of everything, 0.0 degrees Celsius. So now I have my equation. So all three parts, 0 is equal to all of this. And so I'm going to go ahead and simplify everything. I'm going to start my equation over here so I have room. So notice here, when I simplify this, I multiply these together. Joules here, it stays. I have moles. Moles are going to cancel out here and here. And then grams cancels out here and here. So I end up with joules. So when I multiply this together, I get, what do I get? Negative 25,454. So this is going to be negative 25,454.6 joules. Okay, and so remember, here we had 2 sig figs, here we have 4, and so when we multiply and divide, remember that our answer should have the same number as the least number of sig figs. So 2 sig figs is the least number, so I'm only cutting it up there, but I'm going to keep everything else because of, rounding and all that stuff. I don't want to have a rounding error. And so next, I'm going to simplify this. So notice here that grams on top here cancels out grams here. So again, I'm going to have joules left. So I'm going to multiply that together. And when I multiply that, I get 8350. So this is 8350 joules. And again, this has 3 sig figs. This has 3 sig figs. So this is going to have 3 sig figs. So 1, 2, 3. So that's the last sig fig for this calculation. And then finally, this, I'm going to have to distribute this. I'm going to multiply this together. So I'm going to have grams are going to cancel out here. So when I multiply this together, I get, what do I get? Hold on a second. What do I get here? 1932. So then this is going to be plus 1932. And again, it's going to be joules over degrees Celsius. So joules over degrees Celsius. And this is multiplied by final temperature minus the initial temperature, which is 0.0 degrees Celsius. Okay, so now I'm going to distribute this, and I'm going to add this together. So if I add this together, I'm going to get, what do I get when I add those together? I'm going to get 17,195. So this is 0 is equal to 17,195.6 joules. Now again, with regard to adding the, sorry about that. Now, with regard to adding, remember the rule is that your answer should have the same number of decimal places as the least number of decimal places, or whatever one has the least amount of precision, right? So here, the precision, or the last significant digit in this one, is in the thousands place. The last significant digit here is in the tens place. This has less precision. Your answer can't be more precise than the least precise. So that means that the last significant digit is going to be here. So I add those together. This is going to be negative. Okay? And then I'm going to distribute this. So this times this is just going to give me plus 1932 joules per degree Celsius multiplied by TF, the final temperature. And look here, 1932 times this, right? This is 0. The degrees Celsius cancel out. I would end up with joules, but it's going to be 0 joules. So 0, we don't have to worry about. So I end up with this. So now all I have to do now is get TF by itself. So I'm going to move this over. So I'm going to add 17,195.6 joules to both sides plus 17,195.6 joules. So now I have this on this side equal to this. So let me go ahead and erase this. I don't need this anymore. So I've got everything I need. So I got plus 17,195.6 joules equal to, and it's going to be equal to this here. So that's going to be a positive 1932 joules per degree Celsius multiplied by TF. Now all I need to do is divide both sides by 1,932. So 1,932 joules per degree Celsius. Divide this by 1,932 joules per degree Celsius. Notice that the joules are going to cancel out, leaving me with degrees Celsius, which is a temperature unit, which is what I'm looking for, because notice this cancels out, leaving me with temperature, the final temperature. So all I need to do is divide these, and when I do, the final temperature is 8.9 degrees Celsius. And notice, remember, I'm only allowed 2 sig figs here. This was, if I remember correctly, this would be 4 sig figs. So 2 sig figs is my answer. So here I have the right answer with 2 sig figs. So this is the final temperature. Notice that didn't go up very much. So that's it for this example. If you enjoyed this, has this helped you in any way understand how to attack these calorimetry problems, then by all means, like the video, share the video, hit that notification bell, hit the like button over here somewhere. Also, make sure that you subscribe to my channel, hit that notification bell. Do me a favor, help me out, help my channel out. When you do, click the bell. When you do that, click all so you'll be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with or a topic you want me to cover, let me know. I would love to do that for you. Thanks for joining me and have a great day.